There is a huge shift underway in computing, and there is no going back. This isn't about better AI models. It's about who controls compute, power, land, and time. Let me show you what that looks like. This is Hyperion, the world's largest AI data center, crushing New York City. Several million GPUs under one roof, eating up to 5 gigawatts of power. This is the story of the world's largest AI factory, and the extreme decisions it takes to build it so fast. I'm an engineer who spent over a decade building the most critical chips for the systems like this one, and I've covered other massive data centers on this channel before. But Hyperion is different. Not because it's bigger, because when we look at compute, power, cooling, network, it breaks all the rules others still follow. And those choices will shape the future of AI and the global economy itself. Subscribe to the channel and let me explain. This story starts with a business that prints cash. For years, Meta used AI where it paid best. Better targeting, better ads, and this strategy delivered. Meta outgrew nearly every major player in digital advertising. But that success created a problem. While it optimized feeds, the AI frontier moved elsewhere. For Meta, money was never the issue. Performance was. Llama models lost the lead. The shift became undeniable when DeepSeek, a Chinese AI lab, beat Meta on key benchmarks. That's when Mark Zuckerberg stepped in personally and narrowed the strategy to two things: talent and compute. Well, you can't buy a breakthrough, but you can buy the odds. Meta spent billions pulling elite researchers out of places they never planned to live. Offers up to $300 million over 4 years. But even the best team hits the same wall: compute. Right now, AI isn't constrained by ideas or algorithms. It's constrained by compute and power. And that, at scale, forces a different kind of decision-making. It's forcing them to make infrastructure decisions so extreme that they make traditional data centers look obsolete. At that point, Meta had two paths: keep renting compute and depend on someone else's infrastructure, or do something no other social media company ever attempted: to build and control its own compute and power. Hyperion was that choice. If this works, it will give Meta the highest amount of raw compute per researcher, and might even put them ahead of hyperscalers like Google and Amazon. But that outcome hangs on a very big if. Because before Hyperion, there was Prometheus, Meta's Ohio supercluster. There was no single campus, no clean design. GPUs came online wherever they could fit, and this included even tent-style buildings. All of that distributed across Ohio, linked with ultra-high bandwidth networks. And this was fast, improvised, and enough to buy time. When the grid couldn't keep up, Meta didn't wait. They went behind the meter, dropped natural gas generators right next to the racks. Every decision was a trade-off. None of them elegant, but it worked. Prometheus bought Meta time. Hyperion is what comes next, centralized and designed to last. At full scale, Hyperion will pull up to 5 gigawatts of power. And that's enough to overwhelm most regional grids. Now just imagine all of this consumed by a single campus for a single task: training Llama models. Before we go further, we have to understand how an AI data center works. Because it isn't just a building full of GPUs, it's something way more interesting. It's a single machine which is designed to turn electricity into intelligence as efficiently as physics allows. Imagine you're about to build a 5-gigawatt data center. The first problem isn't servers or GPUs, it's power. Where do I find 5 gigawatts of electricity when the grid is already sold out? And here Meta was thinking, do we wait another 2 years for the grid upgrades, or do we redesign a data center? And that's exactly where Hyperion gets very interesting. 5 gigawatts actually simplifies your life, because it instantly disqualifies almost every location on Earth. That's why Hyperion landed in northern Louisiana. It won for 2 reasons most sites simply could not match. First, a massive flat megasite with direct access to water and expendable power. Second, speed. Permits fast-tracked. Equipment tax waived. On a project this size, that saves hundreds of millions and months of time. The rural location mattered too. Many places can offer land, very few can offer power, almost none can offer both quickly. Louisiana could. And that raises the real question. Where do we get 5 gigawatts of power? Meta partnered with Entergy Louisiana to construct 3 natural gas power plants sized for Hyperion. 2 of them will sit right next to the campus in Richland Parish. A third feeds in from over 100 miles away through new transmission lines. Together, they will deliver over 2 gigawatts of gas power, backed by 1.5 gigawatts of solar. So you see, Hyperion doesn't connect to the grid, it extends it. But it turns out generating all that power is just half of the story. How do you push all that electricity without frying the grid? So Entergy is building a new electrical backbone. 100-mile transmission lines, substations and transformers sized for a load no city was built for. Power flows straight from the plants into the campus. No sharing. That's how Hyperion will reach 2 gigawatts by 2030 and keep climbing towards 5. But even with power secured and delivered, one problem still remains: time. At the current AI race, the speed of build-out is no longer the detail, it's decisive, and Meta chose to play the speed card. They actually broke the rules data centers treat as sacred. They dropped redundancy. Normally, power in a data center takes the long, cautious path. From the grid, through backup diesel, through battery holes that smooth every spike. Only then does electricity reach the racks. That's how you get perfect uptime and really long project timelines. Hyperion throws that out. No giant battery rooms, no diesel generators for emergency. Because those things don't just cost money, they cost time, permits, and reviews. So that big decision was a calculated risk, because Hyperion won't serve live users. All of that is for training workloads, and those accept imperfections. If power dips, runs pause, state is checkpointed, and later work resumes. At this scale, hardware issues are expected. And actually the software stack is already designed with this reality in mind. So they got many months shaved off the timeline. And this was the change, because Meta didn't just scale compute anymore, it started to rebuild the energy system around it, basically turning from a software company into the energy developer. And the irony is that power gets you to the starting line, but then compute, cooling and networking lock in outcomes for years. And by the end of this video, you will understand exactly why. But before that, here is the upside of all that AI progress. As systems become more complicated and our work too, you don't actually have to carry on everything yourself anymore. And that's something I've started leaning on too, which brings me to this. These are Sintra's AI agents. They're built to take real work off your plate. You know, most AI tools just sit idle. You prompt, you wait. Sintra agents are different. They are proactive. On busy days, I start with Visi, my personal assistant. I will say, Visi, help me to prepare for today's meetings. It pulls from my email and calendar, gives me a clean summary. Who am I meeting? What were my action items from the last time? So I have time to prepare and think about it. For business development, Sintra keeps things moving. It drafts follow-ups, keeps context without me repeating it. And then there is GG for personal development. Small nudges that keeps you focused when the day gets chaotic. What makes all of this work is something called Brain AI. I uploaded my context once: projects, goals, priorities. From that point on, every agent already knows how I think. So when I ask for help, it's spot on. Sintra integrates with Gmail, Slack, Calendar, Outlook, and Notion, tools you already use. And it removes repetitive work, so you can focus on decisions that actually matter. If you are thinking about hiring your first AI employees that never sleep, Sintra makes it surprisingly easy. And you can get 72% off all plans using my code INTECH through the link below. There is also a 14-day money-back guarantee, so you can try it with zero risk. And thank you, Sintra AI, for sponsoring this episode. Now, back to the story. Imagine they've built all that power. But there is a brutal irony in all of that, because the moment electricity reaches the rack, every watt you feed in returns as heat. All that heat trapped inside four walls at densities no building was ever designed to survive. And once you zoom out at Hyperion scale, the next constraint is obvious. It's size. It's 5 miles long, a mile wide. At that scale, forget air cooling. You need water, and a lot of it. AI data centers are actually infamous for draining local water supplies. At full scale, a campus like Hyperion can consume up to 23 million gallons of water per day. That's a city-level demand. It competes with farms, towns, entire regions. And that's why so many recent data center projects have sparked backlash, especially in places like Arizona and Nevada, where every gallon is already contested. Now, 23 million gallons of water per day sounds really terrifying, but this is what the most people miss. At this scale, power generation is the real problem. It multiplies everything: emissions, heat, and water. Those three gas plants we've talked about use far more water for cooling than the data center itself. Together, they can draw up to 700 million gallons per day. That's a 30 times amplification of the data center's footprint. This is the biggest hidden cost of scale. But just consider that heavy industries like steel industry still uses more water, and it pollutes more. So yes, these numbers sound enormous, but relative to regional supply, they still don't break the system. The real risk is what comes next. The data center power consumption is projected to reach 20% of the global energy consumption by 2030. And this means it stops being a regional infrastructure question and becomes a planetary one. Louisiana is one of the most water-rich states in the United States, sitting inside the Mississippi River basin. Hyperion draws water from the Mississippi River alluvial aquifer, a shallow system that recharges quickly. And this 23 million gallons of water per day, it's not like it's used once and it lost. It runs in closed cooling loops. In these loops, roughly 95% stays in the system each cycle. Over time, though, heat has to leave as evaporation. And Meta funds local projects with the goal to restore more water than it consumes by 2030. Everything up to now was a setup, power and cooling just to get you to the line. But none of that matters if silicon don't scale, because that's where the real money gets burned. And here is what's interesting. Meta doesn't bet on a single chip. Alongside with NVIDIA GPUs, it will run its custom silicon. What's interesting, each of these two is built for a different job, with the goal to squeeze out the most performance for every dollar spent. Meta's in-house designed silicon is called Meteor, Meta Training and Inference Accelerator. It's designed to do repetitive and expensive work extremely well. Things like recommendation systems, ranking, embeddings, and large-scale inference. Under the hood, it's a grid of small processing units running in parallel. And the key idea is simple: reuse data more, move data less. Meta's chip keeps data close to the compute, cutting costly memory traffic. That matters because recommendation workloads are mostly sparse. Large portions are zero, repeated, or barely change, while moving the data back and forth to the memory burns more energy than the math itself. Metas avoids that waste, and they come to a much higher performance per dollar. That custom silicon alone cuts cost by half comparing to running the same workloads on GPUs. And that was the first reason for the custom silicon. The second is control. With its custom silicon, Meta controls how memory is accessed, how data moves, and how software maps onto the silicon. And this is a huge win for efficiency, and it reduces dependence on external vendors. And most importantly, it frees NVIDIA GPUs for one thing that matters the most: training. That's actually where all the heavy lifting is happening. And for that, Hyperion will mostly rely on the latest NVIDIA Blackwell Ultra GPUs. If you crack open one of Hyperion's racks, the structure becomes clear. Each of them contains 36 NVIDIA superchips. Every superchip combines one NVIDIA Grace CPU, which is ARM-based and handling orchestration and data flow, and two Blackwell Ultra GPUs, doing the actual training work. NVIDIA Blackwell GPU is built on TSMC's 4nm process and delivers over 20 petaflops of FP4 compute per chip. Under the hood, each Blackwell GPU uses a dual die design, which is related to the reticle size reaching the limits. Here you can see how two large compute dies are linked by a high-speed die-to-die interface, moving data at roughly 10 terabits per second. To make this tight connection between two computing dies possible, NVIDIA relies on TSMC chip-on-wafer-on-substrate L packaging technology. This is a very interesting and very popular advanced packaging technology which allows you to pack multiple silicon components like compute dies and memory and interconnect and bond them into one shared silicon interposer. In this case, it integrates two computing dies alongside with 8 stacks of high-bandwidth memory into a single package. Then, two of these superchips sit on each compute tray. 18 compute trays make up a rack. Above them, 9 NVLink switch trays tie all 72 GPUs into a single unified fabric. And the beauty of it, that each GPU can talk to any other GPU at full speed. And from the software perspective, it will be seen as one giant GPU. Each of these racks pulls roughly 140 kilowatts. That's the moment when scale snaps into focus. Just think about it. At roughly 2 gigawatts, you're already looking at 14 to 15,000 racks. And if we push toward long-term 5 gigawatt number, that number climbs past 30,000 racks. And that puts Hyperion into the ballpark of roughly 2 million GPUs at the full build-out. Of course, real power budgets include all the infrastructure margins, cooling overhead, and conversion losses. But even with conservative assumptions, the conclusion doesn't change. The numbers are enormous. And that's even before the land, building, transmission lines, power plants. Yes, the campus is expensive, but the silicon bill is bigger by far. It's up half of the data center costs. NVIDIA is not selling GPUs, it's selling the infrastructure. Consider that each rack costs several $1 million, and this puts the compute costs alone in the range of tens of billions, which would be roughly $20 to $30 billion as an estimate. And then power is the second largest expense, and everything else exists just to keep those racks alive. But still, at this scale, the network sets the speed of intelligence. Here, Hyperion links its GPUs with ultra-high bandwidth fabrics, so overall it behaves less like a traditional data center and more like a giant AI supercomputer stretched across open fields. In a nutshell, this is the biggest difference between a data center and an AI data center. We've discussed how power feeds it, how cooling keeps it alive, and how compute does the math. But the network is what turns all of it into a single brain. And if you fail any of these four, the whole system collapses. That's both the beauty and the brutality of building something so complex as Hyperion. Now, from this story, 3 lessons stand out. First of all, AI, frontier AI, is now an infrastructure problem. Leading models don't come from clever code alone. They come from land, power, grid, and years of planning. The second lesson is, right now scale defines the relevance. And if you don't have enough compute and you can't deploy it fast enough, ideas don't matter. And the third, probably my favorite, speed beats elegance. This is a shift, and this is why Hyperion matters. If you look around, Google owns data. Anthropic dominates enterprise and coding. XAI stunned everyone with the construction speed of Colossus 2 data center in Memphis. OpenAI leads in closed models, and Hyperion is Meta's huge bet, a direct response to OpenAI lead and the Stargate project. And this is a very expensive bet. In total, Meta will invest over $100 billion in the build-out, and the current assumption is that more scale equals more intelligence, and that is not guaranteed. Eventually, Hyperion may become the blueprint for how AI is built going forward, or become a very expensive mistake. And here is the most uncomfortable part, because they built this massive data center to optimize engagement and attention, to make apps better at capturing and holding our focus than ever before. All these millions of GPUs will be computing the better algorithm at capturing and holding our attention. So over time, it will be harder and harder to defend. The sad part is systems optimized for engagement don't care why you stay. But I do. I do care that you stay on the bleeding edge of what's coming next in technology. And if that's why you're here, subscribe to the channel. Now, if you want to go deeper, watch this insane story about XAI Colossus 2 data center in Memphis, or this one to learn what it takes to build this semiconductor factory from scratch. Right now, it's a very intense period in my life, and I really admire all your support. Love you guys, and I will see you there. Ciao.